Kia ora koutou. This video is going to go through 2 trig identity questions from old A-level papers. So the first one's a kind of classic identity, the second one is really a rearrange and solve an equation. I'm not going to do the equation solving part in this video, just the identity stuff. So hopefully this won't be too long. The first one though I'm going to do in 2 different ways because I think that a lot of you probably won't spot the fast way. So the first one goes like this: prove this identity. So on the left hand side we've got sine squared theta cos squared theta, and on the right hand side we've got cos of 4 theta. So things to notice: well, when you see that cos of 4 theta, you should be thinking about your double angle rules, but it's not going to be cos of 2 theta straight up, it's going to be cos of 2 times 2 theta. And then the thing that will make it easier if you spot, but you might not be at this point in the year yet, is that whenever you see a sine squared theta cos squared theta, a sine theta cos theta, the trig identity that should come into your brain is this one, that sine of 2 theta is equal to 2 sine theta cos theta. Okay, so that's the preview of that question. And then the second one, which is from winter 2004, is to show that we can take this equation and we can rewrite it in this form. Now, why would we want to do that? Well, if we need to go on and solve this equation, it's far easier to solve a quadratic than to solve the first version of it there. So when you look at this, there's really only one thing to do with this, and that is to use your compound angle identities on both sides and then to do some rearranging. So both of these questions I'd say are at the straightforward end of A-level problems, but definitely worth doing, and make sure that your working's good with no running arithmetic. So let's start with the first one. So we're trying to prove that sine squared theta cos squared theta is equal to 1/8 of 1 minus cos of 4 theta. Oop, don't know what's happened there. There we go. Right, so if we're going to do this the good way, we're going to spot that on this side we've got sine 2 theta is equal to 2 sine theta cos theta. So when I'm doing things like that and they don't kind of form part of the proof, I will often put them into a little box off to the side because we want our working to flow pretty smoothly. So left hand side, sine squared theta cos squared theta is equal to 1/2 sine 2 theta squared, which gives me 1/4 sine squared 2 theta. Now this is where I have to do another little bit of working, and what I'm looking at this time is I'm looking at this thing here, cos of 4 theta. So I know that when I've got the double angle for cosine, that cos of 2 theta is equal to 1 minus 2 sine squared theta. So cos of 4 theta is equal to 1 minus 2 sine squared 2 theta. And what I'm seeing in here is that I've got sine squared of 2 theta here, and I want to end up here with a cos of 4 theta. So this is going to be my link up. So again, working off to the side, not in the flow of it, I get 1 minus cos of 4 theta is equal to 2 sine squared theta. Sorry, 2 sine squared of 2 theta. And 1 minus cos of 4 theta divided by 2 gives me sine squared of 2 theta. So again, I'm putting it off there like that. That way I'm showing the person reading what I've done, but I'm not interrupting the flow of everything here, but I'm also not looking like I've done a huge jump. So here I've got 1/4 of 1 minus cos 4 theta over 2, which equals 1/8 of 1 minus cos 4 theta, which is what I had to show, equals the right hand side as required. So there you go. And if I hadn't put all of this stuff in and I were doing a proof, I would say that you're not making a clean enough explanation from here to here. Okay, but there's a little bit of judgment in there. Alright, now I'm going to do the slog through it another way as follows. So let's go back up to the start and just pretend that you didn't see that sine of 2 theta thing. What could you have done instead? Well, what you could do is just kind of work with the cos of 4 theta. So that's what we'll do now. So we're going to start on the right hand side. And we've got 1/8 of 1 minus cos of 4 theta. So that's 1/8 of 1 minus cos of 2 times 2 theta. So that's obvious. And now I've got a choice to make about which cosine double angle I use. And it doesn't really matter here. I've got both sine squared and cos squared theta where I'm trying to get to, so I can pick either one. So I did this, 1/8 into 1 minus 2 cos squared 2 theta minus 1. Cleaning that up gives me 1/8 of 2 minus 2 cos squared 2 theta. I'm going to take out the common factor of the 2 and get 1/4 of 1 minus cos squared of 2 theta. Now I'm looking at that and I've still got a double angle in here, and on the other side I don't, so I'm going to do another double angle go. So we've got, so this is why this way is definitely more work, right? But I think it's how quite a few of you probably are going to still think about the question. So here we've got this. So cos of 2 theta is 2 cos squared theta minus 1, and I've got to square that. So we've got to expand out a quadratic. Like that. Cleaning that up, a little bit of stuff starts to cancel. I've got 1/4 into -4 cos to the power of 4 theta plus 4 cos squared theta. And the 4's can come out, giving me cos squared theta minus cos to the power of 4 theta. And we're just about there. So we're back to the easy AS stuff now. We've got the Pythagoras identity coming up in a minute. There we go. And we've got cos squared theta, sine squared theta, which is the left-hand side as required. Okay, so that's the first identity question, and that's the harder of the two. So this next one I just wanted to chuck in to make you do a little bit more practice. We're going to show that that first equation can be written in the form of a quadratic. And this is really just good practice at using your compound angles on tan, because sometimes we forget about those ones. Right, so we're starting with this. So because it's an equation, not an identity, it's not really that I'm starting on the left and working to the right. I'm manipulating both sides, and I want to end up with this. Tan squared of x minus 6 tan x plus 1 equals 0. Okay, so we're going to go from here to here. So the way I'm going to do this is first I'm going to write down the identities that I'm going to use here. So that's going to reduce mistakes. So tan of a plus b is equal to the tan of a plus the tan of b over 1 minus tan a tan b. And then the next one is tan of a minus b, which is symmetric, right, because tan is an odd function. So we get this. Okay, so all we're going to do is rewrite these using those identities. And remember, tan of 45 is just 1. So let's just set it out nicely. We start with this. On the left hand side I get this. Again, it's a show that question, so please do show that, don't just jump to the end. Some of you are definitely still doing that in your assignment work. And here we've got 2 times the identity, the compound angle. Right, so now we're going to substitute in 1. We get 1 plus tan x. Quite a nice wee question. 1 minus tan x equals 2 times 1 minus tan x over 1 plus tan x. Right, what can I do? Well, I've got two fractions. I'm going to cross multiply, and I can see the quadratic starting to come, so you should be feeling pretty good at this point. Right, 1 plus 2 tan x plus tan x squared. Oops, I've lost a square there, equals 2. I'm going to expand this in my head. So it's 2 minus, instead of 2 tan x, it's going to be minus 4 tan x plus 2 tan squared x. I'm going to collect everything up and get it to the right hand side. So we have tan squared x minus 6 tan x plus 1 as required. Okay, that's all for now. There are lots of great trig identity questions in the Delta textbook, and there are some in the A-level textbook, but the old Delta has got lots and lots of good practice. Remember, the only stuff we haven't done yet is the stuff on sums to products and products to sums, but everything else is done. Thanks for watching.